All right, great. So yeah, this is some work I've been doing really intensively over the last 10 years or so. And it's been, I mean, as Father Mary said, I'm really interested in applying hylomorphism to contemporary science, especially quantum versions of chemistry and thermodynamics. I really think that philosophy of chemistry is an underappreciated area in philosophy, has a lot of important implications that indicate, I think, what a lot of people in philosophy believe about the sciences is not, in fact, accurate when you look at the philosophy of chemistry. And it's also, let's see, can I get my slides to advance? Having a little trouble with that too, again. Um, okay, let me stop again and try, let me start over again. Sorry about this. Okay. Can you see it still?
Not yet. It went away. It has come back yet.
Okay, let's see. Okay, how about that?
Still don't see it yet.
Okay.
All right, there it is. And then I think if you
Okay.
just click project from there, we should be able to see it.
Okay. How about did it go to the next slide?
It did, yeah.
Okay. All right. Good. Good. I think we're ready to go. Super. So here's an overview. I'm going to talk about why we need inorganic substances. I mean, it's much more hylomorphism has been done on biology, organisms, and the human person. This is natural to focus on these cases, I think. It's where hylomorphism really pays off for us. But to have a complete picture of nature, we need to say something about the inorganic world as well. Then I'm going to talk about why quantum particles in particular can't be substances. And so then that will leave the question of what sorts of things could be a substance in this kind of world. The philosophical role of substantial form. So that's going to be a slight digression into some purely philosophical issues involving hylomorphism. And then the substance of the talk really is in the fourth part where I'm going to talk about quantum mechanics in particular. So again, there's some philosophical groundwork that has to be laid in terms of what a substance is, why we shouldn't have embrace what's typically called emergence, and then what are the world substances from my perspective. So what is it to be a substance? Ousia in the Greek. Here I think of four features we want to look for. We want a substance to be something that exists in the most central focal sense of the word, that at least the creatures are capable of, the sort of fundamental building blocks of the world. They constitute the unique fundamental level of created reality. They have per se unity. They're unified in some very strong sense, and they're the principal ground within nature for change and persistence. So the sorts of things that we study scientifically really depend on substances. So on this picture, composite substances, including organisms and human persons, are not mere heaps of atomic, subatomic parts. So the biological form, in the case of an organism, the soul, contributes irreducible powers to the whole organism. This includes the usual things, perception, voluntary movement, for human beings, rational knowledge and deliberation. And this is not a form of dualism. So the soul, the form, doesn't really do the thinking. It enables the whole embodied person to think. Now, an alternative view to hylomorphism that doesn't embrace reductive materialism or even perhaps non-reductive materialism is called emergence. So in this picture, you have emergent entities or fundamental entities like you and I, but we also contain other fundamental entities as material parts. So we see this in Van Inwagen and Tim O'Connor and others. So my particles are fundamental. They're substances essentially, and I'm a substance as well, even though I'm made up of these smaller substances. Now, there's a lot to be said about this, but here are two problems that hylomorphists find with this approach anyway. One is it seems to lead to a kind of overdetermination of a lot of physical properties, and including physical location. I mean, my particles are all there, and then I'm there too, in addition somehow to the particles. And also, there's even, I think, a bigger problem about accounting for the causal powers of the whole. It seems that you have a kind of dilemma here in that either the whole person is just epiphenomenal, and all the causal power is really possessed by the more fundamental parts, the particles, or you have a kind of something approaches really to a kind of dualism, where the whole person has some powers, and then the problem is how those powers interact with the parts, interact with the atoms. You come very close to a kind of Cartesian picture of dualism here, where the soul is interacting with the physical world in a kind of pushing and pulling sort of manner. So the Aristotelian answer is that substances do not have other substances as parts. So all of their parts are either virtual or integral. So the parts are not fundamental. They're dependent upon the substance in one way or another. So what's a virtual part? Well, a virtual part is something that's a part of a substance. It's a material part of substance, but it exists only potentially, not actually. And then some of the properties, including powers, that would belong to the part, if it were to exist actually, belong instead to Y, restricted to some region of Y's location. And most importantly, for this transfer of powers from the potential parts to the actual substance can be explained in terms of 1, 2, and 3. That is, can be explained in terms of the fact that the substance has these virtual parts. So the virtual parts, even though they're not actual, they play an explanatory role in accounting for the powers that the whole substance has. And I'm going to argue that things like bits of water, fat, protein, and so on in a living organism are all examples of such virtual parts. Now, an integral part, in contrast, is something that's an actual material part of a substance, but it can't exist except as part of Y. This is what Aristotle calls the homonymy principle. So hands and eyes, for instance, are integral parts of the human body. They can't really exist except as parts of the human body. There's no such thing as a completely autonomous hand or an eye. And physical particles are going to be either actual or virtual parts, either integral parts or virtual parts on my picture. So here's a sort of overview of how I would classify the different parts of a substance. So again, we can distinguish between actual and virtual parts. So the cells, organs, tissues of an organism are actual parts, but they're integral. They're subject to the homonymy principle. The cells and organs don't really exist except as parts of the body. Particles and atoms can be actual integral parts, but only when they're activated by virtue of interactions with non-quantum systems. So they have a very short-lived existence as actual integral parts. For the most part, elementary particles, including atoms and molecules, are merely virtual parts of the whole substance, and they're also integral parts. That is, they're tied to the substance essentially. Now, on the other side, the things that are not integral parts, that have a kind of independence in definition or origin, this would be really only in the bottom right category here. So thermal substances like water and protein and so on that exist in my body exist only virtually. So there isn't really any watery substance or protein substance in my body that exists only virtually. There's just integral parts, cells and tissues and so on. Now, the fourth category, these are things that are not actually independent in definition or origin. That's why it's in italics. Remnants of extinct substances. They can be independent in persistence. They can still persist even after the substance is extinct, but they don't have an independent reality or independent origin or independent definition. So you might ask, well, how can a virtual part, if it's merely potential, explain actual phenomena? I think the crucial thing here is that for Aristotle and for the whole Aristotelian tradition, the potential is not the same thing as the unreal. To say that something's potential is not to say it's not really there. It's just a figment of our imagination. The potential is a part of reality. It's just not the primary or the focal part of reality. So the potentialities of the quantum world exist in a state of radical vagueness and indeterminacy. There are infinitely many alternative histories all going on simultaneously, but all existing in potentiality. So quantum entities therefore lack definite and persisting identities and definite locations and trajectories. That doesn't mean they have no location. It just means they don't have unique locations, right? Actual things have to have unique properties and unique powers and unique locations. Potential things aren't restricted in that way. So the chemical structure and the intermolecular interactions still matter, as long as they operate in the same way in each of the alternative histories. So I sort of gesture here towards Feynman's sum over the histories methods. So in one sense, the molecules and atoms and particles are not there. They're not there actually, but they are there potentially. They do exist within all of these potentially real alternative histories that are going on simultaneously. This is not perhaps essential to the talk, but I have written a little bit on remnants of substances. So some accidents and some integral parts can survive even when their substance ceases to exist. So we can see photons from extinct stars. We can have cells and organs from deceased donors, and so on. However, none of these things could pre-exist their substances, so they can't have an independent origin. And that's because their very definition of their nature is tied to the substance from which they are derived. So now I want to start transitioning to at least mentioning quantum mechanics, which is obviously the point of my talk. And the causal relevance of potentiality is really the key discovery of the quantum revolution. And Werner Heisenberg recognizes this in physics and philosophy. So as a consequence, chemical substances, inorganic substances, are largely homoeomerous. That is, except when the virtual parts are actualized. They're a continuum of the virtual presence of quantum particles. So the particular, the sort of atomistic aspect of nature pertains to the realm of the potential, not to the realm of the actual, in my picture. So what are the world's substances? Well, as I mentioned at the beginning, organisms are paradigms of substances, especially for Aristotelians. But the tiling constraint that Jonathan Schaffer has proposed requires that reality be completely composed of substances. There shouldn't be any non-substance parts of reality, except perhaps for remnants of substances, but they're still tied, essentially to substances in some way. So since organisms don't comprise all of reality, all of the material world, there must be inorganic substances out there somewhere. And so the question is, what are they like? Right? Well, I want to say they're not quantum particles. Several reasons for this. One is the lack of individuality as reflected in statistics. This isn't a knockdown argument, but the most natural way to explain things like Bose-Einstein statistics, to explain why these three states, both up, one down, and both down, are treated as the three possible states given equal probability, as opposed to classical statistics, where you'd have four states. You distinguish between A up, B down, and A down, B up. Those would be two different states, right? But in Bose-Einstein statistics, they aren't counted as two distinct states. The best way to understand that, I think, is to think that these particles lack individuality. They're just sort of counters rather than distinct individuals. And secondly, the number of particles is frame dependent in relativistic quantum field theory. So there isn't a frame that is a frame of reference independent number of particles. And that really suggests that they're not in the realm of actuality, but merely potentiality. And of course, particles, at least on standard interpretations of quantum mechanics, lack definite boundaries and trajectories. And so that's the sort of thing that also suggests that they're not really substances. All right, so part three, the philosophical role of substantial form. Again, this is a bit of a digression into some pure philosophy of nature. I'm going to talk about Plato's views, three crucial questions about form, and why forms are not structures. So here's a sort of classic picture of Plato's theory of forms. There are forms of various things, tables, justice, the cat, and so on, up in Platonic heaven. The difficulty with this, of course, is that Plato's forms don't have definite locations in space and time. And as a result, they're really limited in what they can do. They can't explain the per se unity of a composite substance, right? You need something that's located here and now to explain why my parts compose a single substance, why your parts compose a distinct substance of the same kind. And they can't explain persistence. They don't really persist again in a particular stream of events in the natural world. So what Aristotle does is he sort of immanentizes Plato's forms. The Platonic forms become individual essences. And the forms are still involved in explaining similarity within a kind. And I could go into that in more detail another time or in the question and answer period. They're not located in some other worldly domain. They're not in many places at once. So the forms are not external to the substance. There's no strange sort of action at a distance involved. And this provides also an easy explanation for the structure of things like genera, species, and differentiae, which again I could talk about in further in the question period. So here's some crucial questions about forms. Are forms universal or particular? So in my view, they're particular in nature and universal in the mind, which I think is also Thomas's view. Are forms simple or complex? That is, do forms have parts? I think no. Every form is simple, has no parts. Are forms ontologically prior to the substance of which they're form, of which they are the form? So the question here is, does the form explain the existence and nature of its substance? Or does the existence and nature of substance explain its form? Or are the form and substance really the same thing, just considered under different aspects? And my answer to this is A, that forms are actually prior to the substances of which they are the form. They explain something. They explain the nature and the existence of the substance itself. So, what are some of the functions of form in Aristotle's picture? First of all, they do explain similarity. They're a solution to the problem of the one over the many that Plato proposed. They're the ground of the synchronic per se unity of composite wholes. They explain what unifies a composite whole into a single thing. And then finally, they're the ground of the persistence, the diachronic unity of changeable substances. So what makes me the same person I was yesterday? It's the persistence of the very same form throughout time, through that period of time that grounds that. Okay, so that's all the philosophical presuppositions. Now I'm able to get into the substance and talk about quantum mechanics. So I'm going to, again, do a little bit clearing of the ground with a section on tokens and types, and then talk about algebraic quantum theory, the continuum limit, and the persistence of chemical form as some of the key elements here. All right, so one thing we have to distinguish, and I think this is it's a particularly confusing when we deal with inorganic substances, is we have to distinguish between token substances, which Aristotle calls the primary substances or primary ousiai in the categories, and the substance types, the species of substance that he calls the secondary ousiai. So here's some examples of token substances. Socrates, right? The individual human being Socrates. Bucephalus, a particular horse, Alexander's horse. A particular drop of water, a chunk of granite. The sun, probably, right? Here are some substance types: human being, horse, water, granite, star, and so on. So I'm primarily interested in the primary substances. So I'm not just going to focus in this talk on what are the primary substance or what are the inorganic substance types out there, right? Is water a type of inorganic substance? Is granite a type, and so on. Well, I'm more interested in the harder question, which is, when do you have an individual substance of that type, an individual token substance within the type? A harder problem, actually. So my view is that a token chemical substance is a body with thermodynamic, and chemical properties. Right? So this is why individual atoms and molecules are not chemical substances. They don't have, in and of themselves, at least typically, thermodynamic, or chemical properties. Right? They are, however, virtual integral parts of chemical substances, both virtual and integral. That is, they're in the realm of potentiality rather than actuality, and their very existence is tied to the substance of which they are parts. Their definition is tied to it as well. So organisms, like you and me, we have chemical substance duplicates as virtual parts. Bits of water, bits of protein, bits of fat, and so on, that would be chemical substances if they existed outside the body. But they don't, and they don't exist actually in us either. They exist only virtually in us. It's only this human substance that exists in actuality, and it's integral parts like cells and tissues, because no substance contains another substance as a part. So now I'm going to focus on algebraic quantum theory and the distinction between finite Hilbert spaces, which the quantum chemist Hans and philosopher Hans Primus called pioneer quantum theory, and then infinite systems and modern algebraic quantum theory. So in what Primus called pioneer quantum mechanics, you represent a finite system by means of a vector in a single high-dimensional, perhaps even infinite space. And each unit vector in that space corresponds to a property, an observable. This could be used to represent systems with finitely many degrees of freedom, to use the technical term. And all the quantum observables, in fact, all the observables in this picture are subject to complementarity into the Heisenberg uncertainty principle. So that means except when they're observed, they can enter into states of superposition. Yeah, so and that's and in no two observables here are well, many observables are not mutually commutable in this kind of picture. Now, the Stone-von Neumann theorem demonstrates that any two complete representations in these kind of separable Hilbert spaces, Hilbert systems, are unitarily equivalent. What this means in practice, at least for quantum chemists and people doing quantum thermodynamics, is that any vector in such a state represents the same macroscopic state. And so these kind of separable systems are useless for chemistry and thermodynamics. They don't have disjoint superselection sectors that could represent distinct chemical and thermodynamic properties. And these separable systems do not allow for spontaneous symmetry breaking. And a particular important case of that is phase transitions. So in these separable systems, you can't have symmetry breaking and you can't have phase transitions. So you can't talk about the transition between liquid and solid, let's say, or solid and gas. So the solution that quantum chemists and thermodynamics dynamicists rely on is to move to infinite algebraic systems. So in an infinite or non-separable quantum system, the Stone-von Neumann theorem fails. And these systems all have infinitely many degrees of degrees of freedom and infinitely many subsystems. And now we can have inequivalent representations, Hilbert spaces that can represent macroscopically distinct situations, like different phases of matter, different temperatures, different entropies, and so on. Now, to get to an infinite non-separable representation, what we do is we take the thermodynamic or continuum limit of a system. So in effect, we treat the system as if it contained an infinite number of infinitesimally small molecules or other particles. And this fits the Aristotelian picture very well. So in reality, each chemical substance is a continuum of virtual parts with no internal boundaries or discrete actual parts. The individual atoms and molecules are only virtual parts. They exist only in a realm of potentiality and might say intrinsic vagueness. Now, there are three reasons for taking an infinite limit in physics. One is just for mathematical convenience. Sometimes it's easier to do the calculations at the infinite limit. The second one is in order to isolate some factors from others. So we might take friction to zero, for instance, which in a way is a kind of infinite limit because we're interested in other forces and want to ignore the friction. But the third reason to go to an infinite limit is to introduce new structure into the representation. And then when people in quantum chemistry and thermodynamics go to the continuum limit, it's for this third reason. Right? It's not just for mathematical convenience. It's not because they're trying to isolate some factors from other factors. It's because without going to the continuum limit, you don't get the new structure that you need in order to adequately represent the phenomena. So as I mentioned, you don't get spontaneous symmetry breaking in so-called pioneer quantum mechanics when you don't go to the continuum limit. As Strokey described in 1985, if you balance, if this sort of thought experiment where you perfectly balance a pencil on its tip, in simple quantum mechanics, it won't fall in one direction or another. It will fall in all directions simultaneously. There isn't the possibility of slight fluctuations causing a spontaneous symmetry breaking as there was in classical physics, and also as there is when we go to the infinite limit, to the continuum limit. So without spontaneous symmetry breaking, you can't have any kind of distinction, any kind of representation of the distinction between different phases of matter, like solid, liquid, and gas. This is noted by Sewell, Liu, Richu, and actually many others. So what we can do then with quantum chemistry, is we can restore classical properties to the world. So going back to Bohr, people often talk about the Copenhagen interpretation, and obviously that must be referring to Bohr because he's the one from Copenhagen. But I think at least there's at least three different views about what the three different interpretations that go under the name Copenhagen. One is the sort of shut up and calculate model of Feynman. A second one is really the mind collapses the wave function model that really came from von Neumann and Wiener. And then the third one the thing that's really actually Bohr's view comes actually quite close to holomorphism, comes quite close to Aristotelianism. Bohr contended that the quantum theory did not exhaust reality, that reality consisted of two distinct domains, a quantum domain and a classical domain. So the quantum realm didn't make sense on its own. Quantum mechanics always entails the probability of certain classical results of measuring quantum systems. Now, the problem for Bohr is that the world doesn't seem to be neatly divided in this way. Some systems display both classical and quantum characteristics, like supercooled fluids, superconductors, or modern quantum computers. But algebraic quantum mechanics really resolves this problem in Bohr's approach. Because in algebraic quantum mechanics, with its infinite models, we can distinguish between classical and quantum properties. So we don't have to distinguish between two different kinds of systems or two different kinds of entities in the world. We can distinguish between two different kinds of properties that natural bodies or substances have. So each system has a classical center of mutually commuting properties that are not subject to Heisenberg uncertainty or to superposition. So even though the world consists of entities that have both kinds of properties, there are properties, including these chemical and thermodynamic properties, that are not quantal in nature and aren't subject to uncertainty principles. So this is one way, of, at least, of solving the measurement problem. On the Aristotelian view, quantum wave functions are associated with the quantal and virtual parts of substances, representing their powers of interacting with other substances. So a wave function collapses whenever one of those powers is activated through an interaction with another substance. Now, doesn't require consciousness. This is where it's different from von Neumann and Wiener. It's not that you have to have a human observer to collapse the quantum wave function. You just have to have a thermodynamic system. So I often describe it in terms of if we think about the Schrödinger cat problem, right? Intuitively, the cat collapses the function, the wave function, so that you end up with either a live cat or a dead cat. You don't get a superposed cat that's both alive and dead. But the same thing will happen if you replace the cat with an ice cube, right? You can't have an ice cube that's both frozen and melted at the same time. Those thermodynamic properties also do not enter into superposition, and those will also force a collapse of the wave function. So collapse is not a spontaneous bottom-up process, as in GRW or in Penrose, and we don't need to posit any new unobserved mechanisms. So here I'm relying on some work by Wolfgang Smith, early work on this on a book he called The Quantum Enigma, and then more recently, George Ellis and Barbara Drossel. Ellis, a very distinguished cosmologist and physicist, and Drossel, another physicist from Dusseldorf, have worked on a model called contextual emergence, in which it's thermodynamic and chemical properties that are responsible for collapsing localized quantum wave functions. So this helps to explain why we get the persistence of chemical form. So again, to get molecules that are both right-handed and left-handed, at some point you have to have spontaneous symmetry breaking in order to produce, because these are not symmetrical. But again, in pioneer quantum mechanics, you don't get any symmetry breaking of this kind. It only happens at the continuum limit. So to get persisting forms that are breaking this symmetry, you need to go to the infinite continuum limit. It's because the Schrödinger equation for a finite system is spherically symmetrical. So there's no explanation in any physicalist bottom-up way for the emergence and the persistence of chemical structure. So in other words, chemical form, and also I would say thermodynamic form, the chemical form of a chemical substance is really identical to its substantial form. Chemical form grounds the classification of a chemical substance by means of natural kinds in terms of its chemical composition. It grounds the persistence of a chemical substance as the same substance over time, and it grounds the substance's active and passive powers in interactions with other substances. So it makes an irreducible contribution to the powers of these inorganic substances. We can't explain what the substance is doing in a completely bottom-up way from the level of the particles going upward. You need to have the chemical form to structure those particles in order to get the kind of changes that we see in the natural world. So let me just close with a couple problems for my view. You might say, well, but if particles are not substances, if they're always merely virtual parts and perhaps occasionally actual integral parts of chemical substances, what can I say about the Big Bang, about the early early state of the universe. Didn't we have a situation in the early universe where the universe just consisted of quarks and then later just of hydrogen atoms and so on, protons? Where were the inorganic substances there? Well, in my view, chemical substances did not form in the early universe by aggregating fundamental particles in some ways. Chemical substances were there at the very beginning of the Big Bang. The Big Bang, this kind of cosmic atom, as Lemaitre put it, was one or perhaps a very small number of chemical substances, which then disaggregated into particles and eventually into things like galaxy clusters, galaxies, and so on. So rather than thinking of the history of the universe as being a gradual clumping of little things into bigger things, we should think of it generally as a disaggregating of really big things into smaller things. Another tough problem is the individuation of these chemical substances. So where does one chemical substance end and another begin? How many chemical substances are there? How big or small can they be? So I know Stephen Barr's pressed this with me. How many chemical substances in the oceans of the Earth are there? Are the oceans of the Earth all just one gigantic chemical substance, or are there seven, or a billion, or a trillion? Well, I think these are ultimately empirical questions, and our study of collective phenomena of this kind is still in its infancy. So we need to postpone philosophical stipulations here until we know a lot more about these things. Now, chemical substances, I think, can occur at any scale. As I mentioned, they can be at cosmic at scale. They can also be microscopic, in fact, even very, very small. But even when a substance is very small, consisting of a single particle, or even a fraction of a single particle, there's still a metaphysical distinction between the substance with its classical properties and its purely quantal component, or the thing that composes it in that particular case. So I'm not claiming that you get a thermal substance when you put together 17 particles. That's when, I don't claim there's any kind of boundary there in terms of size. Substance can be of any size whatsoever. But the crucial thing is they have classical properties, and quantum particles, as such, do not. Quantum particles have only quantal properties, ultimately. All right, so again, I'll just close by mentioning a few sources that people might look at. Father Mariusz mentioned my book. It's not forthcoming anymore. It's 2022 or 23, Thomas's Philosophy of Nature Obsolete, and I go into this in some detail there. William Simpson has a new book. Again, it's not forthcoming anymore, from Cambridge University Press on hylomorphism. There's a chapter on all of this. We've mentioned one of our books. There's also a book that William Simpson and James Orr and I co-edited on the theology of nature, and then the work of Drossel and Ellis, I think, which you can get by Googling. It's also, I think, very helpful.